Guys, we've been talking. You've been asking, but we've been talking sort of around what we're going to talk about today. So we've been at times the question has come up, why is this an acid? What is it that makes that acidic? Why is this basic rather than acidic? Guys, questions like that. And so today what we're going to do is we are going to ask and answer that question at the level that we need to understand it. So guys, functionally, the question, and don't write this down, but functionally the question that we're going to talk about is this. So guys, why is HCl a strong acid? Why is HF a weak acid? Why is sodium hydroxide a base? Why is acetic acid a weak acid? And why is methanol an alcohol? So, guys, what do all of these molecules have in common? Let me get out of the way. What do all these molecules have in common? They all contain hydrogen, right? So, guys, functionally, where did my notes go? I know I printed them. Did I leave them at one of your places? This is going to be a tough day to... That's really odd. I'm going to have to. And I'll be okay for a second. I'm just going to print these in the background. Bump, 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 bump. Oops, bump, 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 bump. Okay, so guys, functionally, the idea then is this. They all contain hydrogen, but the trick is they all deal with their hydrogen atoms very, very differently. So guys, what does this do with hydrogen? Gives it away completely. What does this do with hydrogen? Gives it away partially. What does this do with hydrogen? Nothing. What does it actually do? Gives away hydroxide. What does this do with hydrogen? Gives it away partially. And what does this do with hydrogen? Nothing. It does not give away hydrogen or hydroxide, making it what? Reviewing for the AP test. What is the name for something that dissolves but does not dissociate? A non-electrolyte. Okay? So, guys, the question then becomes, why do these things handle their hydrogen so differently? And guys, what do you suppose the answer is? Why do they handle hydrogen so differently? Structure. But what does that structure then functionally change? Say it again. Not where. There's a better, say it again. What it's connected to, but it's even a little different than that. It's not, it's how it's connected. Guys, it's a question of how, because all of these molecules have a bond between the hydrogen and the rest of the molecule. So guys, let's talk about a universal principle. What kind of bonds will create stronger acids? Weaker bonds. Guys, it's critical that you understand that. And guys, I'm glad that you're interested, but your enthusiasm is turning into distraction. I'm more than happy to just let you read this from the book and you can sort it out. But guys, let's keep the engagement still appropriate. So, guys, we understand that this is a function of the type of bond that exists. And universally, guys, and we're laying foundation here, universally the idea is the easier that this bond breaks, the stronger the acid will be. Does that make sense? So, guys, let's back that up. What do you know about that bond? Weak or strong? Really weak. What about that bond? Kind of weak. What about that bond? Nutty strong. But what do you know about that bond? Ionic. What do you know about that bond? Kind of strong. What do you know about that bond? Crazy strong. What do you know about that bond? Also crazy strong, and it doesn't do anything. Now, guys, as we have this conversation, generically, you now understand it's about hydrogens bonded to things. And guys, we give that bond a name. We call it the H star bond. And guys, that's the language we're going to use, and that's where we're going to get started. So guys, let's talk about this H star bond. So guys, the H star bond is a bond where the star represents some other atom or molecule. We saw examples of that previously. Could be Cl, could be H, could be NaO, could be CH3O, could be CH3COO. All of those are our stars. Now guys, as we have these conversations, what you're going to find out is this. Thinking about the nature of that bond, the strength of that bond, is an oversimplification. Guys, you are actually going to have to keep track of 3 factors. But not only do you have to keep track of 3 factors, you have to keep track of the context in which those factors are more important. And this we'll talk about as we go. But guys, first of all, let me lay out for you what those 3 factors are. And guys, the first factor is the polarity of the H star bond. And remember, polarity is simply an unequal sharing of electrons. We talk about dipoles, we talk about polar covalent bonds, that sort of stuff. So guys, what is polarity a function of? Electronegativity. And we'll get to that in a minute. But it's actually, we're going to think about it, well, let's do this just to set the stage. So guys, as we go, let's just do the halogens. As we go down a group, what happens to their electronegativity? It goes down. Do you remember why? They're bigger. Good, good, good. They're bigger, more shielding, right? That's the way we're going to talk about it. But guys, coming back to this idea of polarity then, which types of bonds do you think will break more easily? The ones that are really polar or the ones that are more equally shared and less polar? The high polar ones. Guys, the more drifted, the more polar a bond is, the more susceptible it is to breaking, and as a result, the stronger the acid will be. So guys, the more polar the bond, the stronger the acid. So shifting weakens bonds. So guys, factor number 1 is polarity. Factor number 2 is strength. How strong the attraction is. So guys, we've already established this, right? What type of bond strength is going to lead to a stronger acid? Weak, right? So the weaker the bond, the stronger the acid. And then guys, there's one more factor that you need to keep in mind here when you're thinking about the strengths of acids, and that's the stability of the conjugate base. So this may be a good time for you to include this familiar example. Guys, what do you know about the basic strength of the chloride ion? It is, we should say negligible, right? But we've said worthless. Guys, the reason that this is a negligible base is because it's stable. That's actually the way that we talk about it, is the chloride ion is a stable conjugate base. And if you think about it, if you're stable, you're not needy, specifically needy for hydrogens. So the stability of the conjugate base is also a contributing factor to the acidity of a molecule. And so guys, the idea is this: the more stable the conjugate base, the stronger the acid. Okay, so guys, let me explain to you how we're going to progress with the rest of this day. So remember, we had a laundry list of molecules: HCl, HF, NaOH, CH3OH, CO3. What we're going to do is we're going to chip through the larger classes of compounds that those actually belong in. You're going to see they're called binary acids, they're called oxy acids, and then of course we've got the bases, sodium hydroxide. What we're going to do is we're going to go through each of those classes of compounds, and we're going to talk about how these factors influence the acidity or basicity of each of those types of compounds, and then how they actually affect, as they compete with each other, what are the major players and what are the minor players in terms of strength. So we're going to take these factors, we're going to apply them to the different types of acids and bases and alcohols, and figure out how to predict strengths. But Jeanette, I think you had a question first. You okay? Yes. And so yes. So if you look at HCl, it's this, and the thing that makes that stable is it's got a complete octet. Little foreshadowing here. The other thing that you're going to see that makes conjugate bases stable is resonance. Remember when we talked about resonance, that you have that delocalized pi bond that exists all the way around the molecule? That actually creates stability. And did we use this term resonance stabilized molecules? Did we? That's what it means. That when molecules resonate, conjugate base molecules, when conjugate base molecules resonate, it actually makes them more stable and less likely to go back and become the original acid. And we'll talk in a minute. You guys good? All right, so here we go. Guys, let's talk about HCl and HF first. So this is where we're going to start. What do these have in common? They are hydrogens bonded to individual atoms. And guys, there's a name for that. These are what are called binary acids. Bi, of course, means two. One is a hydrogen, the other is something else. So guys, let's sort of tee the ball up here a little bit, right? Let's talk about the halogens. Let's say that our other element is a halogen. HI, strong or weak acid. HBr, strong. HCl, HF. Let's talk about why. So guys, this is the answer to why. So when we talk about, and if you need to write this down, you can, but I think you get it. A binary acid is a hydrogen bonded to another type of atom. Typically it's a halogen. So guys, we call these HX acids. You may want to write that down. Binary acids are what are called HX acids. So what predicts the strength of an HX acid? And the answer is this. The strength, and I want to underline that word. Guys, the strength of an HX acid depends the most on the strength of the bond. So bond strength, remember we've got bond polarity, bond strength, and stability of the conjugate as our three factors. Guys, bond strength is the major predictor. And remember the relationship. The stronger the bond, the weaker the acid, right? So guys, the question then becomes, what determines the strength of this bond? And guys, the answer is this. The stronger the bond, the weaker the acid. And within a group, the strength of this bond increases, or I'm sorry, the strength, sorry. So guys, the idea is this. Within a group, the HX bond weakens as X gets bigger. And that makes stronger acids. So guys, if you want to write this down as a summary, strength is a function of size. The bigger X is, the weaker the bond will be. So guys, let's talk about why. Maybe a good time to also draw pictures. So let's draw HF. So guys, hydrogen has one valence electron. It's in the 1s. Fluorine is 2 energy levels. And guys, consequently, fluorine is such a strong atom. I'm sorry, stop. Such a small atom. Guys, fluorine is such a small atom that the bond that exists between the hydrogen and fluorine is so strong that it's hard to break. And consequently, this is a weak acid. But then, guys, if you do the same thing for HCl, again, we've got the hydrogen with a 1s orbital, and then we've got the chlorine, and it's got the first and the second and the third energy level, and chlorine is actually large enough that the nuclei are far enough apart that that bond is weaker, and it's actually weak enough that water molecules can fully dissociate it, forming hydronium ion as it pulls the hydrogen off, and as a result, that's a strong acid. So guys, the bottom line is this. The primary predictor of binary acid strength is size. The bigger that X is, the weaker the bond will be, the stronger the acid. Does that make sense? You okay with the idea? Okay, so guys, let's stress test the idea. Which will be a stronger acid? HCl or HF? We already talked about it. Which is stronger? HCl, because Cl is bigger. Guys, what about this? Sorry that's so small. Guys, which is a stronger acid? Water or hydrogen? So guys, looking at the periodic table, here we've got O, here we've got S. The question is, which is a stronger acid? And I hear a lot of you saying water, and that's wrong. So guys, which is bigger, O or S? S. If S is bigger, it will form weaker bonds with the hydrogen that will break more readily, making a stronger acid. So HS is more acidic than H2O. Yeah. Yes, but so understand when we say, I'm glad, thank you for going there. When we say binary acids, it's types of atoms and not numbers of atoms. So it's just H and O, but it's 2 H's and O, but it's still related to hydrogen bonded to one other atom. Does that make sense? So guys, do you understand the idea? Do you see now why HS is stronger? Go ahead, Mark. Here we go. Guys, it turns out this is the answer. The answer is no. It works in let's look. So guys, this then is the other thing you need to understand. Polarity is a secondary predictor of bond strength. And guys, we've already established this. Polarity is a function of electronegativity. So the strength of the acid increases as the electronegativity of X increases, because a stronger X, a more electronegative X, creates a more polar bond, creates a bond that's more readily broken. Not because of its strength, but because of its polarity, and those are not the same thing. So now, Mark, rather than talking about groups, let's do periods. You guys ready? You okay? We okay? Okay, so guys, try this. Which will be stronger, CH3 or NH4? And guys, nitrogen. And guys, they're pretty much the same size. Nitrogen's a little bit smaller because it's got another proton. But guys, they're about the same size. So size will not be the predictor of strength. Polarity, as based on electronegativity, will. So which will be more electronegative, the nitrogen or the carbon? Nitrogen, and as you go to the right, they get stronger. So guys, if nitrogen is more electronegative, and it is, the bond with nitrogen will be more polar. And if the bond with nitrogen is more polar, it will be more easily broken, and NH3 will be a better acid than CH4. Does that make sense? Okay, now Mark, to your question. What about these? NH3 or silicon tetrahydride. So we've got NH3 and we've got silicon tetrahydride. Do you see the conflict? Do you see it? So guys, let's talk. If we're talking about size, which one will be bigger, silicon or nitrogen? Silicon. It's got a whole nother energy level, right? So guys, this is the reasoning. Silicon will be bigger, therefore the bond will be weaker, therefore the acid will be stronger. But nitrogen is more electronegative. Therefore the bond will be more polar, therefore the acid will be stronger. So guys, based upon size, silicon wins. Based upon polarity, electronegativity, based upon polarity, nitrogen wins. So what trumps what? And guys, the answer is size trumps polarity. So silicon tetrahydride will be the stronger acid because size trumps polarity. So guys, it goes like this. This is the overall thought. The strength of a binary acid, and guys, I'm really glad Luke said this. Binary acids are not just the halogens with hydrogen, but it's one other atom with hydrogen. Could be NH3, could be H2O, could be H2S, but it's one atom bonded to hydrogens. And guys, strength, which is a function of size, trumps polarity, which is a function of electronegativity. You guys good on that? Clarifications. Y'all okay? Okay. So guys, now we're going to shift gears and we're going to talk about the next type of acid that we need to explore. And guys, these are what are called oxy acids. Not surprisingly, guys, now we got oxygen in the game, right? And this conversation is going to allow us to talk about, don't write these down, CH3OH, CH3COOH, and then also NaOH. And guys, these two are the fascinating conversation. Because here we've got hydrogen bonded to oxygen, and it's an alcohol. Here we've got hydrogen bonded to oxygen, and it's an acid. Why? And we're going to talk about that in a minute. But guys, let's pick off the sodium hydroxide first. So building up to that, it goes like this. Oxy acids are acids that contain one or more OH groups. And guys, your brain goes to OH, that's hydroxide, those are bases. No. They could be, but what we're saying right now is we've got an oxygen bonded to a hydrogen. Or you could think about hydrogen bonded to oxygen. So guys, the trick though is that these OH groups also exist in bases, strong bases. So guys, the question then becomes this. I don't think you need to write it down. But the question then is this: acidic or basic? And the answer is, we need to think about this, and don't write this down, but draw the picture. We need to think about what we call a YOH bond. So we're going to think about it like this, and I would encourage you to write this down. So guys, in the same way that we had an H star bond, and star was whatever it wanted it to be, and then we said HX, X was an element, now we've got Y, and Y stands in for all sorts of different things, now bonded to OH. So guys, the question then is this: what determines whether this will be an acid or a base? Well, guys, when you pull on a chain, where does it break? The weakest bond. So, guys, if the weakest bond is this one, what's it going to be? A base. And if the weakest bond is this one, it's going to be an acid. So now the big question is, what determines which bond is weaker? Well, guys, the idea is this. This is sort of our fixed point. Hydrogen bonded to oxygen. So what we're really asking is, what happens to that bond? What about Y changes the strength of that bond? And guys, here's your first scenario. Y is a metal. I'd encourage you to get this in your notes. So guys, if Y is a metal, what do we know about metals? Chemically. Big or small? Big. Weak or strong? Weak. Yeah, they get beat up by everybody and give away their electrons, right? So guys, metals are these big, fat, homely, electron-losing atoms. So guys, if that's the case, regardless of oxygen being bonded to hydrogen, when oxygen saunters up to this metal, what's oxygen going to do to this metal? Thumpify it and steal its electrons, right? Oxygen will actually completely transfer an electron from the metal. And guys, when it does, what's the charge of this become? Right. Becomes hydroxide. What does the charge of that become? Positive, because it lost an electron to the oxygen. And guys, what did we just create? Salt, right? We've got positive ions, we've got negative ions, we've got ionic bonding, we have a salt. So guys, when this is the case, when Y is a metal, we just formed hydroxide ions, we just formed a salt. And guys, when we form salts, what's the weakest bond in the substance? Is it, well, maybe we should say this, maybe you're not tracking. Guys, what kind of bond is that? Ionic. Aha! Oh yeah. That was exciting. Whoa, that was even more exciting. There we go. So we're one more here. So guys, the idea then is this. This bond right here is ionic. What about that bond right there? Covalent. Which is going to be weaker? The ionic bond. It breaks at the ionic bond, and we have a metallic base. You okay? Questions on that? Okay. So guys, let's play with the other scenario. What if Y is a nonmetal? This isn't in the notes, but if you want to write it down, you can. So guys, now Y is a nonmetal. What does that now tell you about the size and strength of Y? Small, strong. So guys, if Y is small and strong, can oxygen steal from it? It cannot. Consequently, this bond will be ionic or covalent. Covalent, and therefore stronger. So now we need to talk about what this is going to do. And guys, it plays out like this. When we talk about this now covalent YO bond, hydroxide is not easily formed because that bond between the Y and the O is strong. So guys, these substances are either going to be acids or they're going to be neutral. And if they're neutral, those are called alcohols. So guys, this is where this gets interesting. I explain the logic to my students with about 50% success. But I'm going to try. So guys, we're talking about this, right? I'm going to just pose this as a question and let you chew on it. So guys, we're now talking about a Y-OH bond. This is covalent, this is covalent. Remember, we've got three factors, right? We've got strength, which is a function of size. We have polarity, which is a function of electronegativity. Don't worry about factor number 3. We'll talk more about that in a minute. So guys, let me ask you this question. Why can bond strength not be a factor in the strength of an oxyacid? Let me say it again. Why can bond strength not be a factor for the strength of an oxyacid? I want to just give people a moment to chew on this. Allow me to ask again. Why can bond strength not be a function? Why can it not be a factor in determining the strength of an oxyacid? Give you a second to think about it. Doug, what are you seeing?
So if it's an oxyacid, then the weakest bond is the OH bond, and that never changes.
Why?
Because it's the same for all oxyacids.
Why?
It's weaker than the other bond.
Right, but why does it never change?
Because
What's the hydrogen always bonded to? Oxygen, right? I had to get that out of you. Guys, this is the reasoning. Remember that strength is a function of size, right? The size of what? Not the hydrogen. Guys, the strength of this bond is a function of the size of what? What hydrogen's bonded to. Remember, guys, we drew these pictures down. Where'd it go? There, right? Guys, size is, when we say that strength is a function of size, it's the size of the thing that the hydrogen is bonded to. And guys, if we are talking about, where did it go? There it is. Guys, if we're talking about an oxyacid, what is the hydrogen always bonded to? Oxygen. So the size of the thing it's bonded to can't change, therefore the strength of the bond can't change. So if it's not strength, what does the major factor, predictive factor, have to be? Polarity. But now you're going, wait a minute. Polarity is a function of electronegativity, and if polarity is a function of electronegativity, and if the hydrogen's always bonded to the oxygen, then the polarity can't change either because it's always the electronegativity of oxygen, right? Wrong. And the answer is this. This guy can pull on the electrons too. Guys, it turns out that if we've got a really electronegative dude sitting on the other side of this oxygen, the electronegativity of this particle can reach across the oxygen and cause that bond to become more polar and therefore increase the strength of the acid. Guys, there's a name for that. It's actually called drift. No, this isn't strength. Strength is size, right? So strength is size. Polarity is what we're talking about now. polarity is what we're talking about now. And if this dude is really electronegative, this bond moves in that direction, making it more polar, therefore more readily broken, therefore making the acid stronger. Is that okay? So guys, the name of that is drift. This is important. As the electronegativity of Y increases, the acidity increases due to drift. So guys, allow me to show you some examples of drift. You may want to include this. Again, I don't know if you need to. You get this, right? The OH bond becomes more polar. It's more readily broken. The strength of the acid goes up. So guys, let me show you some examples. These are two weak acids that we haven't really talked about. Guys, one of these is HClO. I don't think I'm in writing mode. Guys, one of them is HClO. One of them is HIO. So the idea is this. We've got a hydrogen bonded to an oxygen. We've got a hydrogen bonded to the oxygen. The oxygen has the same size. Therefore, the strength of that bond is the same. But, guys, this is what happens. Looking at the periodic table, which is going to be more electronegative, the chlorine or the iodine? Chlorine, right? So, guys, the reasoning is this. Chlorine is more electronegative than iodine. The electronegativity of chlorine is 3, iodine's 2.5. Here's what happens. This chlorine reaches past the oxygen and causes this bond to drift in this direction. Iodine does the same thing. It also causes drift, but there's less drift here because the iodine's weaker, more drift there because the chlorine is more electronegative, it's stronger. As a result, which of these bonds will break more easily? The one on top or the one on the bottom? The one on the top. And we see that represented by their Ka values. Guys, these are both relatively weak acids, but this acid's 1,000 times stronger than this one. And you see that 10 to the 8th compared to 10 to the negative 11th, roughly 1,000 times stronger. The reason is because this electronegative chlorine causes increased drift. Consequently, we have a stronger acid because that bond's more polar. Does that make sense? Because, guys, maybe you're putting this together then. Talk to me about this. Like that. Guys, why is that acidic and not an alcohol? Maybe I should draw an alcohol. You're not that familiar with them. So guys, why is the top one acidic? Yeah, guys, it's drift, but it is not. So look at what we've got. We've got hydrogen, oxygen, carbon, hydrogen, oxygen, carbon. So up to that point, alcohols and weak organic acids are exactly the same. What makes this guy acidic? This. Guys, it turns out that that oxygen can reach around the carbon and around the oxygen and cause this bond to drift. And as it does, it makes that bond more polar, therefore it's a weak acid. Guys, this molecule does not have a highly electronegative element over here. Therefore, there is no drift. Therefore, all of these bonds are relatively non-polar covalent bonds, and they don't break, and that's an alcohol. You get the idea? Guys, there's a name for this. These are what are called, where'd it go? Wait, no, up. Right here. Guys, these are what are called carboxylic acids. And so again, if you want to write this in, the idea is that this oxygen causes drift, making that bond more polar. Now guys, these are carboxylic acids, but in addition to that, that group, that COOH group, is called a carboxyl group. And these are the groups that are present in acetic acid, formic acid, acetylsalicylic acid, aspirin. Oh yeah. But guys, here's the thing that's also interesting. Factor that makes this a pretty good weak acid. There's another one, and I want to show it to you as soon as you're caught up. You guys all caught up? Don't write down the examples of the acids. It's just the three that I thought of. But we did a question. We know about acetic acid. Formic acid is ant spit, and then acetylsalicylic acid, what we're using in the lab, right? I just wrote them down. You guys good? Okay, watch this. Guys, this is interesting. I would encourage you to do this with me. So guys, that is the Lewis dot structure for vinegar, acetic acid. Now, when this breaks apart, it loses a hydrogen, right? And what are we left with? Acetate. So now guys, let's do this. Acetate is CH3COO. And when we draw the Lewis dot structure for acetate, we end up with this. We end up with that. But guys, why is this not right? This is not a valid Lewis dot structure. Why not? Carbon doesn't have a full octet. So what does carbon do to create a full octet? Double bonds to oxygen. Which one? Doesn't matter. It's a resonance stabilized molecule. Guys, right? This stuff that you learned that you need to review to get ready for the AP test, when you get in this position, if you could create double bonds in two locations that are equivalent to each other, this is classic delocalized pi bonding. So guys, we would draw this like, oh gosh, we would draw this like this, and then we would draw the other like that. And then remember, we put these in brackets and we draw the double-headed arrow. And guys, that's a resonance stabilized molecule. Remember how we talk about that? It's a resonance stabilized molecule. It has two resonance structures or conformations. It contains delocalized pi bonding. Here's the thing that's interesting. This delocalized pi bond actually causes that molecule to be less needy, if you will, less likely to go back and grab a hold of the hydrogen that it's got, because it doesn't really need it as much anymore because it's found a way to resolve its bonding issues in the absence of the hydrogen by simply creating that delocalized pi bond that allows it to partially complete its octet in the absence of that hydrogen. Guys, that's the other reason that acetic acid is a fairly strong weak acid. Without that resonance stabilization, that would not be the case. You get the idea? Interestingly, guys, there's another example of this. Well, there's many examples, but there's this example. NO3, nitrate, is also resonance stabilized, and that's the foundation of nitric acid. The nitrate ion is so stable. not because it's completed a full octet. Because remember what Jeanette said, right? If we look at HCl, why is Cl so stable? And she came up with the idea that it completed its octet. Well, guys, it turns out that here this is so stable because nitrate is resonance stabilized. Okay. So, guys, that's where we're at. So let's do this then in summary. We can now do the whys. So guys, talk to me about why HCl is a strong acid. Why? Because chloride is big. Chloride is big, so the bond is weak, and it breaks up like crazy. Why is HF a weak acid? Fluorine is small, the bond is strong. So guys, why is NaOH a base? Na is a metal. Therefore, it contains what kind of bonds? Ionic. Therefore, the weak bond breaks and it releases hydroxide. Why is CH3COOH a weak acid? Drift caused by the other oxygen. Why is CH3OH an alcohol? It doesn't have a strong enough other atom bonded to the OH to create drift. Therefore, these bonds are strong and relatively nonpolar, not easily broken, and this is a non-electrolyte. It's an alcohol. Yeah. You don't need to go there. Yeah, it'll be apparent. Yeah. You guys okay? Okay, so guys, finally this, and we're not going to spend class time on it. This is up to you. You will see a couple questions on the AP test about Lewis acids and bases. Ready for Lewis acids and bases in 12 seconds? Bronsted, Lowry, Lewis. Acids, bases. Guys, Bronsted, Lowry, what do acids do? Give away positives. What do bases do? Take in, oh, poop. Went the wrong way. Guys, what do bases do? Take in, so maybe I should be careful with my arrows. That's in, and this is out. So, Lewis was an electron guy. Electrons are negative. Because electrons have the opposite charge, they will also have the opposite direction. So Lewis acids are thought of as substances that take in electrons. Lewis bases are things that are thought of as giving away electrons. Now guys, if you'd like to see an example of this, consider this. NH3, nitrogen, hydrogen, hydrogen, right? And then 2 electrons here. In the Bronsted-Lowry sense, this is a base, right? Because what does this do? What does this do to water? Takes in a hydrogen. This takes in a hydrogen, and consequently it gives away OH. Because guys, if you're thinking Bronsted-Lowry, you're tracking the hydrogens. But if you're thinking Lewis, you're looking at the electrons. And what does NH3 do with electrons for hydrogen? Gives it some. So guys, it's exactly the same definition. It's a change of focus. In Bronsted-Lowry, you're looking at the protons. In Lewis, you're looking at the electrons. But the results are the same. So you will see a couple questions in homework about this. If you choose to do them, great. If you don't, that's your choice. But understand, you may see a couple questions on these relative to the AP test. Here's your homework.